Hey everyone, welcome to another video. I'm Shruti, and in this video, I'll be doing a rapid, quick, simple revision of machine learning concepts. And let's get started. What I'll be doing is I'll be making a Google Doc side by side and jotting down some notes so that I can come back and refer to it later as well. And yeah, let's get started. I'll be sharing my screen. Yep. Oh, just had to refresh my page because some network issues were happening. Um, okay, so I just listened. Okay, what else? Precision. Give me 2 minutes. I'll refresh my screen. Everything's slow. Okay, so precision, recall, F1 score, ROC, AUC curve, use accuracy. This F1 versus AUC, confusion matrix, interpretation, offline versus online evaluation. And also think about ML system design or end-to-end workflow, like problems like design a recommendation system, search ranking, fraud detection, or we can have feature stores, training pipelines, serving infrastructure, handling real versus real time versus batch inference, model monitoring, observability, data drift, and retraining strategies. Then there can be resume based too. Questions like maybe walk me through a project you build. What was biggest win or failure in ML project, or like real time as well? How did you improve model performance? Trade-offs you made and why? Alright, so this can be one part. Another part could be coding, which is like ML based. So that we can have maybe implement an algorithm or gradient descent, back propagation from scratch, coder confusion matrix, solve problem, numpy pandas, data manipulation. Write a simple neural network in PyTorch, Keras, or more. Yep. Okay, means this is etc. Okay, so this is what we can think of. So somebody could ask, questions from this maybe. There is also linear algebra, I think. So uh, can be somewhere here. Linear algebra. So let's talk a little bit about linear algebra now. Mm, so in linear algebra, there are few concepts which we will study. I'm gonna make notes as well for myself. So first is, I think, we need to be strong with our size. Okay, strong with our intuition over formulas. Like, could you explain an algorithm to a person who is not in tech or something like that? We need to focus on geometry, rank, traces, and other things like determinant, determinant, dot product, norm, orthogonality, span, etc. So first, let me revise a little bit from my notes and I'll write some concepts. Matrix multiplication. This is basically dot product of rows and columns, and dimensions must align to be able to multiply. By dimensions, I mean m cross n dot. How do I put dot like in the middle? It's okay. It's a dot in middle. Just n multiplied by p equal to m multiplied by p. Yep. So basically, in backpropagation, when we traverse back from our neural network, weight gradients are matrix multiplication. So we say dly dw is x to the power t multiplied by change uh, dy. Not commutative, it's not commutative, so we cannot say ab is not equal ba. Matrix multiplication's disadvantage, actually drawback, is that it is computationally expensive, bottleneck in deep nets solved by GPU. Next we have eigenvalues and eigenvectors. You can say AV equal to, actually, vector V, any vector V only scales, does not rotate under transformation A. So eigenvector talks about the direction, whereas eigenvalue talks about how much it stretches or shrinks. Eigenvalue is a scalar that represents how much character is scaled up or scaled down during a linear transformation. And the formula is something like this. So core concept is matrix A represents geometric transformation, either shear, stretch, or rotation. Eigenvector V specifies a direction that does not rotate the axis during the transformation. So the steps to find eigenvalue of matrix, we subtract lambda from the main diagonal of matrix. How to calculate Eigenvalues and eigenvectors are fundamental concepts in linear algebra. Eigenvalues are scalar values linked to a matrix or linear transformation. They indicate how much an eigenvector gets stretched or compressed during the transformation. The eigenvector's direction remains unchanged unless the eigenvalue is negative. So the equation for eigenvalue is given by AV equal to lambda of V, where A is the matrix, V is associated eigenvector, and lambda is the eigenvalue. So this was eigenvalue. How about eigenvectors? Eigenvectors are non-zero vectors that when multiplied by a matrix change only in magnitude but not in direction. So eigenvalues are found first, and for an n by n matrix A, eigenvectors are n cross 1 column vectors. Okay. Um, let's read through this image that I got from Geeks for Geeks. Insert it here. Insert image, upload. Yep. And this. So let's see, find the values and eigenvector for this matrix. If eigenvalues are represented using lambda and the eigenvector is represented this, then eigenvector is calculated by this equation. So here we have the matrix lambda and then I identity matrix which is 0. Then we solve this and 1 minus lambda multiplied by, so cross multiply equal to 0, and then we find the eigenvalues and eigenvectors. So for particular lambda, we then do this multiplied by v. Simplifying the equation, we get eigenvectors value of a and value of b. Similarly for minus 1. These eigenvectors are this. These are two possible eigenvectors. Many of the corresponding can also be considered. So I'm thinking, why is it even important to study eigenvalue and eigenvectors? Um, I think when it comes to ML and you have concepts like PCA, like algorithms like PCA. So eigenvalue talks about how much scaling is there in a variable or in an algorithm, but it is incomplete alone. So eigenvalue and eigenvector are complete together. So the thing is, maybe one is speed and another is direction. So want to study speed without direction versus direction without speed. We need both because we want to understand the behavior, that if things are growing or shrinking or staying stable while predicting. And differential equations and recurrences, things like that, are solved by solving both eigenvalues and eigenvectors. So real world applications would be Google's PageRank, where there is importance of important pages on the first, and it is done using eigenvector because you could check in ML if the audience of a particular page is growing or not. So that is something like that. Another will be um, machine learning PCA, like most important direction in the algorithm PCA is given by eigenvalue or eigenvector, I think. In quantum mechanics, there are observable values and eigenvalues of operators. In construction engineering or structural engineering, there are different frequencies. Lambda can be frequency, and there are different modes. So if you just use lambda without v, you know that a system is scaling by 5, lambda equal to 5, but you don't know the direction. Whereas opposite, if you just know the v and you don't know the action, you know that it's going towards this direction, but you don't know the scale. So together, both of them, like speed and action, tell you about transformation. So you need both speedometer and a compass, right? Eigenvalue tells us the magnitude of what a matrix does. Does it stretch, compress, flip, or leap? But alone it cannot do so. It needs a eigenvector v that tells it the direction, that okay, transformation happened to the right or only in this thing, not in this thing. So in math, it is really important, I think. Yeah. So apart from this, there is something called eigenvalue decomposition. Here we here we talk about decomposing square matrix into eigenvectors and eigenvalues. Only works on square diagonal diagonalizable matrices. The spelling mistake. Diagonal diagonalizable. Okay. It is useful for understanding transformations, computing matrix powers, foundation for PCA. Not all matrices are square. There is SVD, singular value decomposition. Works on any matrix, not just square. You can see if I have a SVD. I am not a mathematician, so I need to understand what SVD does and why, more than how it works exactly from math perspective. This guy on YouTube gave the human explanation of SVD saying that human matrix maps user to concept correlation sigma matrix that defines the strength of each concepts, and we maps movie to concept relation. He also mentioned two concepts specifically, sci-fi and romance movie. My questions are: how single value decomposition knows the number of concepts? He as human mentioned two, sci-fi and romance, but in reality, resulting matrices are three concepts. For example, matrix U, the one with blue titles, has three columns, not two. How SVD know what is concept after all? I mean, what if I shuffle the columns randomly? How does SVD know what is sci-fi, what is romance? I mean, I suppose there is no rule. Group the concepts first in column order. So somebody gave an answer which I'm gonna read. A matrix maps vectors into another vectors from one space to another space via matrix multiplication. If you multiply the matrix with every vector on a unit sphere, the result vectors will be ellipsoid. The singular value decomposition is an encoding of the sphere and the ellipsoid. The left singular vector are primary axis. Okay, he's going too much into depth, I think. Um, Singular values are primary axis of ellipsoid, and then other are different, are mapped to the sphere. So ellipsoid is mapped to the sphere. Hmm. I still don't understand his question and answer. Okay, I'll try to look for some other easy explanation maybe. SVD is a powerful matrix factorization technique in linear algebra that decomposes any real or complex matrix into three simple matrices. One is rotation, one is scaling, and another is another rotation. It is used in image compression, machine learning for dimensionality reduction. What else do we have? Any matrix M cross N A, regardless of its rank or whether it is square, can be decomposed as this particular formula. One is orthogonal matrix representing rotation, one is scaling, and another is another rotation. Why is SVD so important? SVD acts as a data reduction tool, allowing you to extract the most important information from a noisy or large data set. So, low rank approximation. Because the singular values in sigma are sorted from largest to smallest, they indicate the importance of each ingredient in the data. You can discard the smallest singular values to create a compressed low rank approximation of original matrix. PCA SVD is the mathematical engine behind PCA used to simplify this while regarding key features. Insert, match. Here is the another thing. So it is used in PCA recommender systems like matrix factorization, NLP, and compression. There is also called truncated SVD. Skip top k singular values, low rank approximation, which is LoRa itself. Okay. There is another concept called covariance matrix. This talks about measures how features vary together. Diagonal is variances of diagonal is covariances. When there is symmetric and positive semi-definite ones too. So eigenvector decomposition decompo covariance matrix gives us PCA directions. Covariance measures how two variables change together. If they tend to increase or decrease simultaneously, covariance is positive. Covariance is positive. One variable increases while others decreases. It is negative. So this is both variables are in the same direction. Variables move in opposite directions. Studying our test scores and then outside temperatures and winter codes. No relationship like shoe size and daily intelligence. To calculate it for a sample of data, you must find the difference between each data point and mean for both variables. Multiply those differences and average them. What is the difference between covariance versus correlation? Well, covariance tells you the direction of the relationship. It does not indicate the strength of that relationship. So it is affected by scale of the data. Covariance of 5 means it's something entirely different from a covariance of 5,000. To fix this, statisticians use correlation. Correlation divides the covariance by the standard deviation of both variables, producing a standardized score between -1 and +1 that is easy and measures both direction and strength. Finance used in portfolio theory to diversify assets. Investors look for stocks with negative or low covariance. So if one asset drops, others might rise, protecting the overall portfolio value. Used to uncover feature dependencies, which help data scientists simplify complex data sets like PCA, etc. Right, this is interesting. I didn't know that for diversification, something like PCA is used. There is another concept called principal component analysis, PCA. So I think the Mm. The goal of PCA is to find the directions of maximum variance in the data. The steps are: center the data, compute covariance matrix, do eigen decompose, sort by eigenvalue, and then project. So principal components are basically eigenvectors of covariance matrix equivalently computed via single value decomposition on the data matrix directly. Use case is dimensionality reduction, visualization, noise removal, avoiding multicollinearity. VC is just like taking a photo of 3D object from the best possible angle to capture its shape. Imagine you have a cloud of data points like football floating in a room. PCA finds the longest part of the football. It then finds the widest part. It ignores the thin flat parts that don't matter as much. Okay, I have another example. Imagine you are trying to describe your perfect romantic partner using 50 different traits. PCA helps to realize that most of the 50 traits almost just boil down to just two big vibes. And what is that? Vibe breakdown. Instead of looking at 50 separate numbers, PCA find the main direction of stretch, the soul, and the spark. This combines traits like kindness, shared values, emotional support. PC2 combines physical attraction, shared hobbies, and sense of humor. This is given by Gemini. Nice, interesting. Okay, this is what it says. So we have PC1 and then PC2. What else? So now we have just simple 2D map. You can now plot every person, simplify the data to see the big picture. So it is used for dimensionality reduction, visualization, noise removal, avoiding multicollinearity. We have another concept called vector spaces and projections. Vector space is a set of vectors closed under addition and scalar. Projecting data into principal components is literally this operation. So basically, vector space is set of vectors closed under addition and scalar multiplication. We have something called projection of into U. In machine learning, projecting data onto principal components is something like this. PCA is a linear method, kernel PCA since to Okay, I have three images and we'll go through it together. Right, insert image, load. The YNML high dimensional data lives in a vector space. Every row in your CSV is a vector. Every column is a basis vector. Projection logging. Projecting V into U asks how much of the V points in the direction of U. You project the data matrix X into eigenvector. This squashes the data into most important lines or planes. You might ask, what does it mean for a weight matrix to be rank efficient? All possible linear combinations of the columns. If your model predicts a particular thing, your prediction must live in the column space of X. If the true Y is outside this space, your model will always have errors or residual. The set of all X that becomes 0 when multiplied by A is null space. If X matrix has non-empty null space, it means some feature combinations are totally invisible to the output. This happens with multicollinearity. Orthogonality. In PCA, the principal components are orthonormal, 90 degrees and length 1. Benefit this ensures that each component captures unique info with zero overlap. What is the relationship between rank and dimensions? Rank is the number of linearly independent columns. If rank is less than minimum of m of n, the matrix is rank deficient. Linear regression is finding orthogonal projection of target vector onto the column space of feature matrix X. Okay, need some clarification more. I think more clarification. Mm, There is another concept of inverse matrix. So, inverse matrix is it exists only if A is square and non-singular. That is, determinant is not equal to 0. And multiplication of a matrix A and its inverse is like gives us the identity matrix, right? In ML is used in closed form solutions like normal equation for linear regression. Okay, I have another definition for this. Might be easy to understand. In the world of ML romance, the inverse matrix is quest for the perfect match, the soulmate condition existence. An inverse only exists if the matrix A is square and non singular. Square, what does it mean to be square? You both need to be on the same level, that is, same number of rows and columns. Non singular, you must bring unique value to the relationship. If one of you is a copy of another or collinear, this is just machine learning, this is not real, like extremely real, I would say, in terms of ML romance. You must bring unique value to the relationship. If one of you is just a copy of another, determinant becomes zero and the spark disappears. You become singular, work on yourself, and the inverse cannot exist. What is the perfect union? When you find your inverse, the result is the identity. In romance, it's like finding the person who perfectly undoes your chaos and brings you back to the true self. You neutralize each other's complexity. What is collinearity and normal equation? In linear regression, we use normal equation to find the best weights. If your features are cheating, meaning they are too similar, measuring age in years, age in months, the matrix becomes singular. The math breaks. You cannot invert the matrix. It's like relationship where you both agree on everything so much that you don't have independent identity. The fix, pseudo, inverse, and regularization. When the perfect match does not exist, we did not give up. The good enough X, it's not a perfect inverse, but best possible fit when tail does not exist. Or regularization, adding a little personal space to the diagonal. It forces the matrix to be invertible by making sure no two features are too identical. If your features are collinear, your model's heart will break because it cannot find inverse. Okay. There is another concept of orthonormality. So, vectors are orthogonal if they are perpendicular. PCA components are orthonormal. Orthonormal. No redundancy between components. Rest gradient descent behaves better in orthonormal spaces. There is another thing called diagonalization. Diagonalization when we is of this formula. There is perspective and the core. Perspective is the set of eyes, eigenvectors. P is like basically eigenvector. You need to see the person clearly. D is the diagonal matrix. It contains the eigenvalues. It's the person in simplest form where their traits don't overlap or interfere with each other. So this is the formula. In a long-term relationship, raising a matrix to the power of n, it is exhausting to calculate the complex version over and over. If you know their core, you just grow that core and then switch back to your normal perspective. It is computationally cheap and emotionally efficient. Matrix similarity. Same person, different output. Two matrices A and B are similar if they are actually the same romantic partner, just behaving differently because of the environment. Same soul. Similar matrices share the same eigenvalue, determinant, and rank. Different look. They might look like different matrices because they are being viewed through a different lens. In neural network, when you change the basis of your hidden layers, like switching from raw pixels to features, you might be performing a similar transformation just in a different coordinate system. Interesting. Yes, this is for today some basic concepts and revision. We listed down the main important topics that are I feel are important. For part one today, these are some basics that I think are nice: matrix multiplication, eigenvalue, eigen decomposition, singular value decomposition, why is SVD important, covariance matrix, covariance versus correlation, PCA, vector spaces and projection, inverse matrix, pseudo inverse and regularization, orthonormality, diagonalization. Okay, this is it for today, guys. Thank you for joining me. Bye. See you. Thank you.